Welcome to the PhotoModeler Vehicle Crush tutorial. In this tutorial, we will determine crush measurements on a vehicle using photographs taken from an unknown camera. Since nothing is known about the camera that took the crush photos, to be able to solve this project, you must have some known coordinate information about points on the uncrushed part of the vehicle. This exemplar vehicle is surveyed to extract 3D coordinates to use as control points, which are needed by PhotoModeler's inverse camera to solve for the unknown camera parameters. This information could be measured using traditional survey instruments such as a total station, or in this case, PhotoModeler with a calibrated camera was used as a surveying tool to extract the 3D coordinates from the exemplar vehicle. Any method that can generate an accurate set of 3D coordinates can be used as a source for control points. Here is a completed example project, done with a calibrated camera of an exemplar vehicle. This process is similar to the steps outlined in the points-based walkthrough tutorial video. The project uses 6 photographs taken from a good variety of angles. The residuals are low and the project is solving well. Some measurement checks were done against the exemplar vehicle. This ensured a strong result and therefore a good set of control points, which in turn increases our chances of a good inverse camera result. We export the project as a DXF file, which will be used as our control data for processing the photos from the unknown camera. We go to File, Exports, Export Model, and select 3D DXF. We make sure point IDs are on and save the file as Corolla exemplar.dxf. Next, we start a new project to begin work with the photos of the crushed vehicle from an unknown camera. We choose a standard project, browse to the folder with our images, and add them to the project. Since we do not know anything about the camera that took these crushed photos, we choose an unknown camera solved by control points. We click Next and get a pop-up telling us that an inverse camera description cannot be shared by 2 photographs. Since we do not know anything about the photos, we cannot assume that they were taken by the same camera or the same focal length settings. This message tells us that a copy of the camera description has been made. We now have 2 cameras in the project, each assigned to a separate photograph, allowing them to be solved independently. This message also tells us the focal length flag has been set. This means that the focal length option in the photo properties is set to be solved for with inverse camera processes. In certain cases, you may want to solve for the principal point as well as the focal length. This may be necessary if you think the photographs have been cropped and the image is off-center. Solving for principal point requires a very strong set of control points, and you should try solving for just the focal length first. The format aspect ratio is not often solved in inverse camera, and only solve for it if you suspect there is a scanning error or some other problems that would affect the squareness of the pixels. To set these other parameters for solving in inverse camera, use the Photo Properties dialog. When working with photos from an unknown camera, something needs to be known about the scene, so PhotoModeler can back calculate information about the camera. In this case, we will use known 3D XYZ locations imported as control points. To add the control points, we open the External Geometry Explorer and select Add Imported Object. The units for this file are inches. We select the Corolla exemplar.dxf file we exported from our exemplar vehicle project. This data could also come from a third-party survey or other source. We choose Fixed to ensure the control point coordinates are not adjusted during processing. This is suitable when you will mark a low number of control points. Since we included point IDs with our export, we would turn on text fields for point names. Click OK, and the project units are set to inches. You can see we have a fairly detailed model of an undamaged exemplar Toyota Corolla. This model actually contains more detail than is normally required for control point projects, but this detail will help demonstrate other aspects later in this tutorial. If we scroll the list, we see that all the points have ID numbers. There's also a name column. The ID numbers are sequential numbers for the points as they come from the file. The name field comes from text entities in our DXF file. In this case, the numbers are the point IDs from the exemplar project. If we used the renumber command before exporting the exemplar DXF, the 2 IDs would match up. You can see some IDs have a text describing the point. These particular points have been named in the exemplar project to help us identify these points more easily when we mark the control points on the photos. For example, this point 107 in the exemplar project, is named DS front rail, which is short for the front part of the rail molding that runs down the driver's side of the car. We select the front rail point. If we switch back to the 3D view, you can see the front rail point is highlighted in green. You can select points in either the 3D or list view. We open photo 1 where the point is displayed. We switch to import marking mode and move over photo 1. The cursor switches to the import marking display, and we use Alt Zoom to take a closer look and mark this point. Next, we will mark this point here. Incorrect or inaccurate control point marking will give poor results in inverse camera processes. If you mismark a point, you can adjust its position in select mode. Next, we mark this point. It is very important that the control points have good coverage on the photo. You want to try and have control points marked across the photo rather than all bunched in one area. Especially when solving for focal length, you should also have some points with varying depth. Otherwise, you may get poor results or inverse camera may not solve at all. All our points so far are covering this one plane of the driver's side. This point, passenger side C-pillar bottom window, represents a point on the other side of the car. This can be viewed through the windows. We now have some depth coverage of the photo. Enough points have been marked for the project to process. The camera's position and inverse camera focal length have been solved. This processing has been done using the minimum number of points. If the points marked did not have sufficient spread across the photo, you might get an orientation failed message. In this case, you should confirm the points marked so far are accurate and correct. You may need to mark some more points to strengthen the project before orientation will succeed. Here, on photo 1, we have marked some additional control points on undamaged parts of the vehicle to strengthen the project solution. We have reviewed our marked locations and checked the residuals to make sure the project is solving relatively well. Another check we can do to ensure the project is solving correctly is to turn on the 3D projected model and check that it lines up with the photos. Go to Visibility and turn on Imported Points and Lines. Overlying the photo are the lines from the imported control file. We study the photo to see how well the control file matches the vehicle in the photo. The marked control points have been used to lock the rest of the control file in place. Of course, the projected lines in the front areas will not match the crushed area in the photo, but the uncrushed area should match correctly. We check how well the lines match up along the windshield, windows, and doors. Everything seems to line up well. We'll turn off 3D display and open a point table. Our review of the marked placement improved our residuals. In an inverse camera project, residuals can be judged differently. Unlike standard reference points, in this project we are solving for the camera parameters using control points that are set so their coordinates cannot be adjusted. If we are not 100% sure they are marked in the exact correct positions, this results in higher point residuals. For these types of projects, residuals around 10 pixels are still acceptable, but lower would be better. When they start to hit 15 pixels and above, you should review your control points to see if they are positioned correctly. The residuals in this project are acceptable, so we close the point table. We can now mark control points on photo 2. Close photo 1 and open photo 2. Switch to control point marking mode. Again, we start with points that are easy to mark and have a good spread across the photo. Start with this point here and add points that give good spread across the image. This point here, we can see through the window. This one, we can also see through windows, here. To make sure we have a good spread across the photo, we'll mark this point here. The minimum number of points has been met, and photo 2 is now oriented. We'll mark some additional control points to strengthen photo 2. Here we have photo 1 and 2 marked with a good set of control points. We have reviewed the residuals of the project and things are solving well. We will demonstrate a technique that can be used to verify the project solution. We will switch to referencing mode, mark a point at the cross of this T. We move our cursor to the other photo, which becomes the destination window. The reference helper line, also called the epipolar line, appears. We can see that this line goes through the section we marked. The reference helper line helps us find the intersection where we should mark the matching point. We mark the point at this intersection. We will try with another point. Mark the intersection of the T on the window here. Go over our destination and see if the reference helper line matches up. If the reference helper line appears off target, such as here or over here, this is an indicator that the project results are poor. If this was the case, then we would have to review the placement of our control points and ensure we had sufficient control points with good coverage across the photo. If your project has large residuals and the projections or reference helper line are not lining up, check your control point placement. You should also be sure that the exemplar vehicle that you got your control points from is the exact same model. It should be the same make, year, and model. Even some minor features such as body lines and molding can vary in shape or location in the same model due to dealer options and production variations. Similarly, with a road scene, you should be careful that features you are surveying for use as control points have not moved since the time the original photos were taken. The survey of control points is usually done after the fact, and you want to be sure you are getting the coordinates for the objects that were in the same position at the time the original photos were taken. If we open a 3D view, we can see the imported control object as well as the points we've marked in the photos. Here are the 2 points we just added at the T intersections. To help identify which parts are from our imported exemplar vehicle, we will add a new material. We open the Materials dialog, click and enter the name Exemplar Pink, and choose a pink RGB color for the material. Now we will select a part of the imported control object and change the material for the object to Exemplar Pink. Our marked data is in the default white and our control data now shows in pink. We turn on camera stations and verify they are in an appropriate position. We have performed our quality checks and are satisfied with our result. We can now move on to the next step, which is marking and referencing of our points on the damaged section of the car. Now the inverse photos are solved for, using our control point data, we can continue with the project in the same way we would if we had a calibrated camera. We hold down Control and left mouse drag to zoom in on the area around the crush, on photo 1 and photo 2. We start by marking some of the damaged area of the hood, using Alt Zoom to make sure the points are marked accurately. We'll zoom in here and mark some drill holes and some parts of the bumper and undercarriage. When marking is complete, we switch to select mode and use drag region select to select our newly marked points. When we switch to reference mode, because the points are selected, photo 2 has become the source. And we can reference the selected points on photo 1. We use the epipolar reference helper line to help identify where to mark the references. These points have now been referenced. Our final goal in this project is to get displacement measurements from a profile of the interior bumper shown here. The plastic covering of the bumper has fallen off, so we will use the inner bumper as our source for the crush measurement. We use Image Enhance for a better view of this bumper in photo 2. There are not many distinct points to mark along the bumper. We'll mark a point along the top edge of the bumper near some other identifiable features, so we'll have a general idea of its location when comparing it to the other photo. After we mark a point, we then move the cursor to the other photo and use the reference helper line to find where it intersects the bumper near the feature. We continue marking some key features along the bumper, using the reference helper line to identify the matching